All right, Satmati, you're a PhD in computational neuroscience and you're working on a new company, but like, let's just pause. Like, what is computational neuroscience before we dive in?
So depending on who you ask, it's different things.
Okay.
In my world, it was about understanding how to, at least trying to bridge the gap between human and artificial intelligence.
Okay.
So not to be too much of a Debbie Downer on AI, the human brain is still significantly more powerful and competent than any AI out there.
Yeah.
And so my research was specifically trying to understand what makes the brain so special from a computational and algorithmic perspective at extracting information from the world around us. And when that information highly overlaps with other information, flexibly being able to know when to learn general information about that data that's coming in versus being able to separate it. So like, we all know what chairs are, and I can show you different types of chairs, and you know that they're all chairs that you can sit on. But you're also able to tell the difference between a chair that you sit on normally and a chair that, your partner always sits in, and you don't want to mess that up. So that's something that's really difficult to train an algorithm to do today, but we do it like effortlessly.
Well, of course, we take less data sets or data points to make the same extrapolation, but like we can dump data onto these models in a different sort of velocity than we can dump it into our brain. So like you were in the PhD program pre generative AI being what it is, and you sort of lived through that. So like why so bearish still?
Well, so one of the projects that I got to work on and never got to finish because I graduated too fast was working with François Cholet from Google's ARC dataset. And so that dataset was made up specifically to try to get at reasoning abilities. It's a little different from what I was doing, but fairly similar. And really the idea there was you couldn't just memorize a bunch of patterns, you had to actually understand fundamental ideas of like how to process things, like real, rational, relational sort of understanding. And I think the current leader is in the like low 40% accuracy on the like ARC data set, whereas the least performing humans are at like 85% accuracy on this thing. And we're talking about like something that a 3-year-old could do with a little bit of training. GPT-4 can't like even get close to that sort of ability. And so is it really that we just have that much more data coming in? Are we that much better at processing it? Is there something special going on there? Is it just the architecture of transformer models that just aren't good enough? Because they're great at storing a lot of memory and compressing things and extracting information from that really well. But they don't seem to be able to like learn general principles and reason. Because memory is important, but it's not the only thing that the brain is capable of doing. It like uses that with all sorts of other tools to get at answers. And I think until you like either get really, really lucky or understand how the brain works, which we're really far away from still, it's going to be really hard to get that like, artificial general intelligence. But what you can get are AI models and systems that are exceptionally good at specific tasks and in specific verticals. So that's what we're big believers of.
And I guess as helpful context, we just left the most bullish event on AI possible, I think. And so, you're maybe bearish relative to the pace towards AGI, but certainly not bearish on the application of the transformer technology to solve meaningful problems.
And other like even more classic like machine learning
of course,
sort of perspectives. Like if you have really good data and a good use case and you can figure out, okay, well, how can I use some sort of predictive modeling to get at something interesting or automate something that's, really dumb and repetitive and unlock, greater flexibility for people to use their brains to do more interesting things, go for it. Right? Like, what, if it's okay to talk about this,
Please.
What I'm working on is risk in the built world. Like, how do you understand the risk profile of large infrastructure projects, for instance?
How do you?
It's not easy.
How do you do it how do they do it the old-fashioned way? Then maybe how do you?
So the old-fashioned way is you have a group of engineers working on the bid response team get together And this
like
is,
civil engineers?
Yeah,
Okay,
like civil engineers, not even lawyers, because they're working on what they call a project agreement, and it's this massive dump of PDFs that are hundreds of pages long each, that is a contractual outline of basically the scope of the project and what the risk is. And what they need to do is understand what's going on in that project fast enough and put a competitive price on that when they respond to the bid. And today that involves people that hate legalese, trying to figure out how all these things are interconnected in their contracts, and understand topics, understand where risk is and how it flows. And some of that can involve people that are paid a good salary and are really, really smart, sitting in their office and doing like Control F, searching for specific keywords in all of their PDFs.
That might be the greatest keyboard shortcut of our. That's the most underrated product of ours.
But they should. That's not what those people are like good at. Right, and they shouldn't be doing that. And so, this is a prime example of where you can use AI to speed up a process that unlocks a lot for the user here, which is the person responding to the bid. And so we've, working with this idea that data is really important and vertical knowledge is great. We've taken contracts and transformed them into networks to understand exactly how the different elements of a contract interact. And that is something that an LLM has a really hard time with. But if you mix in the abilities of LLMs to understand some semantic properties, and then you throw in the addition of understanding relationships and links by turning things into networks, using graph neural nets, or even a graph RAG sort of approach, that's when you start understanding relationships in something, and you mix that sort of semantic relationship information, you get at something that kind of looks like some ability to reason and understand logic. At least with how risk flows through a contract.
And I know that's how we got linked up with the event, is we were nerding out on the use of graphs, GNNs. The graph RAG is incredibly, underutilized. We think that it's going to really explode in popularity in the near term. So, tell us, double click on how you guys are using it, how you think it's going to evolve in other use cases, because it feels obvious in this very small room, but it feels like no one else has the level of enthusiasm publicly quite yet.
So this may be a problem caused by being into the brain, but a lot of problems in the world can be turned into graphs or networks, which means that basically throw graph RAG or GNN at almost any problem. Now, that's not always the right way to approach things.
Right.
But anytime you have some sort of complex system that you can model out as a connection of nodes and edges between them. That's the way, right? How else do you learn? If you can predict edges, you can predict new nodes. You're understanding how things connect and flow, right? So any sort of even anything that's sequential, anything that really turns into this sort of network is where those techniques can go. And it's, mixing them with LLMs is also kind of cool. Right? That's
it's sort of funny because this was the source of strength for Google search, right? And everyone
get a PageRank. That's really simple, spectral decomposition of matrices, right?
And we're back to this, this might again be the biggest lift we have from a technology perspective. It's back to this old lesson that we've learned has created $1 trillion plus value 20 years ago. We're just resurfacing back and reapplying it, which it sort of feels like it should have been obvious when the new transformer technology came to be, but it's almost 2 years later now when we're seeing how impactful it is, how you can't just throw everything in a vector DB and hope that it'll find the right understanding. So what's your prediction on graph RAG adoption over the next 12 months?
So it's easy to implement.
Easy.
And the you don't need to understand that much of the math behind it either, right? You just need to understand a graph in its simplest form is super easy, right? It's something's here, there's a connection. I can understand things based on that, right? So intuitively, it makes a lot of sense to people. Not that hard to implement. most of the tech is out there for
Yeah, let's get tactical.
Right?
What's the what do you use in like someone's listening to this and they're like, all right, yeah, actually this does make sense. I mean, for some reason, just using like Pinecone as a vector DB and I'm not getting accurate results. And of course, this makes sense. Like where do they go? Like what do they type into the thing?
Well, we build everything in-house, which may or may not be the right solution. But there's a bunch of like relational databases out there, like a Neo4j, I think is an example of one that I haven't used very extensively, but you can make use of that. And then just once you have your network graph structure, there's a lot of stuff that you can do, like community detection, and then you throw in some of the things that LLMs are really great at, which is understanding some of the semantics and the topics of things, and sort of clustering and linking things together that are semantically related, or talking about the same sort of things. And all that's there, right? Like any open source LLM you want, literally can help you with that. Or if you just want to use like a simple embedding model and then look at where, your the vector of each of your nodes lies in a space, and then just cluster based on that. That's another way of doing it. So you just basically are building up the graphs by having nodes. You just need the main challenge really is not a technical one. It's literally just a modeling thing. Can you define what your node is?
Right.
Like in our case, the clause in a contract, and what a relationship is. Like if you're doing, I don't know, flow of airplanes through airports, right? Like, okay, well, maybe the nodes are different airports, the edges are the actual planes or whatever, and you can put a weight on them based on how many flights there are back and forth. That's the real
challenge.
Crux of the problem.
It's a systems dynamics challenge, right? Like, what is the relationship between these two? Which is like straightforward, maybe for contract, not more straightforward for contracts than it might be for a more dynamic, simulated environment. But unlocking that unlocks sort of the ability to explore the entire information space of whatever you've graphed on a way that's just not possible within another technology. So
and that's really the main key challenge is, can you define what your network is? And then from there, everything kind of unlocks itself pretty easily. Like looking into the right sort of algorithms, like even if you want to first pass, like not even trying to do too crazy complex AI stuff, like can you like measure the centrality of your nodes? There's different ways of measuring centrality, and all those algorithms already exist. And they're really easy to implement, and that gives you an idea of what your graph is really talking about and what sort of insights you can get from it. And then beyond even the like graph RAG approach, you can measure all sorts of properties about it. You can do like community detection, clustering algorithms. You can look at all those centrality measures I was talking about. And those are properties that you can then bake into each one of your nodes. And now instead of just doing like a simple sort of retrieval thing and getting the like relevant subnetwork that answers a user's question, you can go and build your own models based on like graph neural net architectures and embed like if there's text in a node, the semantics of that. But then beyond that, like information about the centrality of that node, like basically like how important it is, all these extra features that you have that can be baked in there and used to train a model. And then the sorts of insights you can get from that are pretty,
so the LLM can crawl the node, but then within the node itself, we can provide a bit more structure in and of itself, and that provides a higher level of accuracy, which is almost always like, the challenge, right?
Like the idea is that you're basically taking your data and constantly using that same data to extract as much information as possible. You're like basically enriching it as much as possible.
With structure.
Exactly. The structure is the beauty, and there's a lot more structure than we think. Right, like you even said a contract's kind of like straightforward, right? But to the normal person, right, like it's just it's a linear flow of text, right? And it has that structure like intuitively in the way it's built, like, but I don't know, if I'm on page 500 and it's referring to like one of the first clauses, I got to go 500 pages back to find it. It's not, it doesn't make any sense, but it literally is super structured. And I think we'll start noticing people catching on more of these like true hidden structures and what seems a little bit more unstructured, and really leveraging that, because that gives you a much more rich data set to work with, and maybe we don't have to worry quite as much about running out of data that fast.
Right.
And then dealing with synthetic data, which is its own sort of can of worms, right? Like if your model's not that great to begin with, and then you're using it to produce data to then help it train, like, is that really that good? And that's an interesting question.
If that can improve, and we can improve structure, then everything lifts, and that's great too. Like that's good. Where can people find more info about you, about the company you're working on?
So you can find us at Enlaye.com.
Enlaye.com. You got the .com.
Yeah, we
went .com too. We went blitzy.com.
No one had the name Enlaye.
Yeah.
And it's a cute story also. My co-founder and I both went to high school.
I love that.
In a suburb of Paris, and it's Saint-Germain-en-Laye. Enlaye.
Okay, very cool.
Enlaye.
I thought it was cool enough that you guys just went to high school, but the company's named after together. I mean, and not went to high school, period. But the fact that it's named after that is pretty cool. Well,
it's really fun.
We're super pumped to follow along with your journey and exchange notes along the way. So thanks, man.
Yeah, my pleasure.